Welcome to the deep dive. Today we're launching into a truly foundational exploration. This is an essential module that governs how every application, database, and operating system interacts with persistent memory.
It really is.
We are diving deep into the physical and logical architectures of storage, starting right at the core with Module 3, Lesson 1.
That's absolutely right. The mission for this deep dive is to establish a rock-solid understanding of the storage landscape. We really need to unpack the intricate components and performance inhibitors of traditional mechanical spinning disks.
The old guard.
Exactly. And then immediately contrast that with the breakthrough architecture of the modern solid-state drive. And this isn't just about, defining hardware.
No.
It's about understanding the bottlenecks that affect every system you design, optimize, or troubleshoot, from disaster recovery planning to maximizing transaction throughput.
We're transitioning from the almost unbelievable precision required to manage microscopic magnetic particles moving at a quarter the speed of sound to the agonizing milliseconds of delay that govern mechanical access time. Get ready, because understanding these physical limits and how modern storage overcame them provides the ultimate aha moment about the hardware beneath your critical applications.
Okay, let's get into it.
Okay, let's unpack this by starting where storage began for most of us. The old guard. The technology that defined the data center for decades. The mechanical hard disk drive, or HDD.
Right.
Before we can even talk about the performance benchmarks, we have to open up the device, metaphorically speaking, and understand what's sealed inside that metallic fortress, what the sources refer to as the head disk assembly, or HDA.
The HDA, or head disk assembly, yes. It's the sealed unit containing all the precision mechanical parts. And it's critical that it's sealed.
Why is that so important?
Well, because even a tiny speck of dust or a microscopic fingerprint can catastrophically damage the components inside. They can cause a head crash. So inside this environment, often called a clean room environment, we find several key components working in high-speed electromechanical harmony. The drive functions by using a rapidly moving arm controlled by precise electronics to read and write data across flat magnetic platters.
Let's start with those platters then, because they are the actual medium that holds all the information, right?
That's where the bits and bytes live. Platters are these rigid circular disks, usually made of aluminum or sometimes glass or ceramic substrates.
Okay.
And they're coated on both sides with a ferromagnetic material. This material is crucial because data is recorded by polarizing these microscopic magnetic areas or domains into a binary state, the zeros and ones we all rely on.
And the key detail here is that they use both sides of the platter.
A fundamental point, yes.
Right.
Every single platter typically utilizes both its top and bottom surfaces for data storage. So the total raw capacity of any given drive is a direct function of the number of platters stacked inside and the areal density.
Areal density, that's how much data you can pack into a square inch.
Precisely. How much data they can engineer into each square inch of that surface. It's a constant battle to increase it.
And those platters aren't stationary. They are moving incredibly fast, which brings us to the spindle and rotation.
Yeah, they have to. The spindle is the central axis. It's the physical rod that connects and stacks all the platters together. It's attached to an extremely precise spindle motor.
And that motor's job is just to spin them at one constant speed.
One constant, very high speed. Its job is non-negotiable. This speed is standardized, measured in revolutions per minute, or RPM. We commonly see enterprise drives operating at 7,200 RPM, 10,000 RPM, or even 15,000 RPM.
The insight here about the sheer physics involved is what always gets me. We're talking about components moving at potentially dangerous speeds.
Precisely. If you actually do the math on the circumference of a standard 3.5-inch platter spinning at 15,000 RPM, which is typical for high-end fiber channel or SAS drives, the outer edge of that platter is achieving speeds around 150 miles per hour. As we noted, that's about 25% of the speed of sound.
That's insane.
It is. This massive rotational speed is necessary to reduce the wait time for data. We call that rotational latency, which we'll cover in a bit, but it also creates immense engineering challenges. You have to balance the parts, manage heat, and crucially, maintain the air cushion that keeps the read-write heads from just crashing into the surface.
Speaking of heads, that brings us to the next crucial components. The read-write heads and the actuator arm assembly. These are the parts that dance above the data, right? Reading and manipulating those magnetic particles.
They absolutely define the precision of the HDD. The RW heads are these microscopic magnetic sensors, sometimes called sliders, that literally fly on a cushion of air created by the fast rotation of the platter.
But they don't actually touch it.
Never. Under normal operating conditions, they never touch the magnetic surface. If they did, it would be a catastrophic head crash, which would generate dust and destroy data instantly.
And these heads are mounted on the actuator arm.
Correct. They're mounted on the actuator arm assembly. This arm moves radially in and out across the platter surface, and it's driven by an incredibly precise mechanism, often called a voice coil motor, to position the head exactly over the desired data location.
So once the physical structure is clear, we move to the logical architecture.
Yeah.
How is all that data organized on the surface of the platter itself? I mean, it can't just be random.
Not at all. It's highly structured. The logical organization relies on 3 foundational structures, which are defined when the disk is low-level formatted: tracks, sectors, and cylinders.
Okay, let's start with tracks.
Tracks are the fundamental concentric rings on the platter surface where the data is actually laid down. You can think of them like the grooves on an old vinyl record.
But they don't spiral inward.
Exactly. That's the key difference. They are perfect circles. They are numbered starting from 0 at the outermost edge of the platter and counting inward. And the density of these rings is measured using tracks per inch, TPI.
So a higher TPI means more data.
A much higher capacity, yes. High TPI means the manufacturer has packed those tracks incredibly tightly. A high-density drive today can easily have hundreds of thousands of tracks per inch.
Achieving high TPI must be incredibly difficult when the heads are floating just nanometers above the surface and the platters are spinning so quickly.
It is the absolute pinnacle of mechanical precision. But the complexity doesn't stop there, because the tracks at the outer edge of the platter are physically longer than the tracks near the spindle.
Right, bigger circumference.
Exactly. Manufacturers realized they were wasting capacity by forcing every track to hold the same amount of data. This led to the introduction of zoned bit recording, or ZBR.
That's a crucial engineering detail that differentiates, I think, an advanced discussion from just the basic definition of tracks. So tell us more about ZBR.
Well, ZBR is where the drive groups tracks into zones concentric bands on the disk surface. And crucially, tracks in the outermost zones contain more sectors than tracks in the innermost zones.
Why? Just because there's more physical room.
That's it, exactly. Because the outer tracks have more physical space. For instance, the outermost zone might have, say, 256 sectors per track, while the innermost zone only has 150 sectors per track.
And the benefit is just more capacity.
A massive capacity improvement, yes. But there's a trade-off. It introduces complexity into addressing, and it means the transfer rate varies depending on where on the disk the data resides.
So you read faster from the outer tracks.
You do, simply because more data is passing under the head per revolution. The data density is just higher out there.
Okay, so tracks are divided into smaller segments called sectors.
Exactly. A sector is the absolute smallest, individually addressable unit of storage. This is where the host reads or writes data. While the number of sectors per track varies because of ZBR, a critical specific detail is the size of the user data payload.
And that's usually 512 bytes, right?
Historically, and still very commonly, a sector holds 512 bytes of user data. Yes.
And this is where the formatted versus unformatted capacity discrepancy comes in, because the sector holds more than just the user's 512 bytes.
That's the key insight. You've hit on it. In addition to the 512 bytes of payload, the sector structure includes significant overhead. This metadata stores things like synchronization bits, the sector number, the cyclic redundancy check, or CRC information for error correction.
A lot of housekeeping data.
A lot. It also includes the head platter number and the track number. This internal information is vital for the controller, but it consumes physical space. This overhead is exactly why a drive advertised by the manufacturer as 1 terabyte, meaning 1 trillion bytes, actually yields significantly less usable formatted capacity for your operating system. Some of that space is dedicated to this essential metadata.
So we have tracks and sectors defining the location on one platter surface. To simplify addressing across the entire physical volume, we stack those tracks vertically to create cylinders.
Correct. A cylinder is a conceptual vertical alignment of all tracks with the exact same radius across all surfaces of all platters in the drive stack.
So it's like a cookie cutter going through the whole stack of platters.
That's a great analogy. And since all the RW heads are physically locked onto the actuator arm assembly, they all move together and are always positioned over the same cylinder number simultaneously.
And that simplifies things.
Immensely. Because instead of tracking, say, 10 different platter surfaces independently, the drive head location can be referenced by a single cylinder number, which vastly simplifies data layout for the controller.
This organized structure historically required a complex data addressing scheme for the host operating system, which used to be the historical CHS approach.
CHS, it stands for cylinder, head, and sector. In legacy systems, the host operating system had to possess intimate knowledge of the physical disk geometry, how many cylinders, how many read-write heads, and how many sectors per track.
So the OS had to know exactly what kind of drive it was talking to.
It had to know everything. The OS would request data by stating the exact CHS coordinate. This worked fine when disks were small and their geometries were fixed and simple.
But the sources highlight that this became completely unworkable as drives grew larger. Why did CHS fail to scale?
It failed primarily because of limitations imposed by the system BIOS and the operating system architecture itself. Early BIOSes had hard-coded limitations on the maximum number of cylinders, like 24 ends and sectors, maybe 63.
So the hardware outpaced the software?
Massively. As disk manufacturers started building drives with thousands of cylinders, the OS simply couldn't address them directly using the physical geometry. And, imagine the nightmare for system administrators.
Ooh, yeah.
If you upgraded your 500-cylinder drive to an 800-cylinder drive, the operating system had to be completely reconfigured to understand the new geometry. It made hardware upgrades incredibly painful.
So the industry needed an abstraction layer, something to hide that complexity.
They did. And that gave us the modern solution, logical block addressing, or LBA.
LBA was the great simplification.
It really was. It moves away from physical coordinates, and it treats the entire disk as one continuous linear array of blocks, numbered 0 up to the total block count. The operating system, the file system, your applications, they only need to know the block number, the LBA address, and the disk's total size and blocks.
So they no longer care how many platters there are or about zoned bit recording.
They are blissfully unaware. They don't care if it has 5 platters or 8. The complexity is hidden.
So who handles that essential complex translation from the simple linear LBA back to the complex physical CHS address?
That is the exclusive domain of the disk controller, the brain of the HDD. The controller receives the logical block address from the host and executes the necessary firmware translation to determine which cylinder, which head surface, and which sector holds that specific piece of data.
And this is where the architectural shift truly matters to our learner. Why is LBA abstraction so fundamental in the modern data center?
It matters because LBA enables hardware independence. It allows the disk manufacturer to change the internal physical geometry, adding more platters, using ZBR, increasing TPI without ever impacting the operating system or applications.
So to the host, a 2 terabyte drive is just a 2 terabyte drive.
It just presents a massive number of logical blocks. The controller hides all the underlying complexity, which is essential for efficient system design and painless hardware upgrades. It's essentially the disk drive lying to the operating system, but in the most helpful and flexible way possible.
That's a perfect way to put it.
Understanding the architecture leads us directly to the Achilles heel of the HDD, its performance limitations. The mechanical nature of HDDs imposes speed ceilings that are simply unbreakable without changing the underlying technology.
Right.
When we quantify how fast an HDD can satisfy a request for data, we look at the disk service time.
And disk service time is the comprehensive measure. The total time from the host requesting data to the disk delivering it back. And it's a sum of 3 critical delays, 2 of which are purely mechanical and measured in, as you said, agonizing milliseconds.
Exactly. Service time is a composite of 3 components. Let's start with the largest mechanical delay. Component 1, seek time.
Seek time, that's the physical movement delay. The RW head has to move radially across the platter to find the correct track.
That's correct. Seek time is defined as the delay involved in positioning the RW heads over the correct concentric track. This is governed by the speed of the actuator arm moving in and out. This delay is the most significant penalty in random access operations, typically ranging from 3 milliseconds on a high-end 15K drive up to 15 milliseconds for slower archival drives.
So if the head has to move a long distance, the seat time goes up dramatically.
It does. It's simple physics.
I recall the sources specify 3 distinct measurements for seek time, which can be a little misleading if you don't know the context.
Yeah, vendors have to be very precise here. So they specify 3 things. First is full stroke.
That's the worst case scenario.
It is. It's the maximum time required for the RW head to traverse the entire width of the disk, from track 0 on the outside to the innermost track near the spindle. It's the slowest measure.
Okay, what's next?
Then you have average. This is the most practical measure, and it's what most people quote. It represents the average time taken for the RW head to move between random tracks. Typically, vendors calculate this as the time required for the head to cover about 1/3 of a full stroke distance.
To represent sort of typical randomized movement.
Exactly. And finally, there's track to track. This is the minimum time representing the single-step movement between two adjacent tracks. This shows the absolute physical speed limit of the arm mechanism itself.
This inherent penalty, the need to physically move the arm, means that performance is just drastically reduced if you're constantly jumping to random data locations.
Which is characteristic of most database transactions.
Precisely. And this limitation led to that fascinating optimization technique you mentioned, the short stroking trick.
Short stroking. It's a brilliant, albeit expensive, compromise where speed is valued far, far above capacity. The technique involves partitioning the drive so that data is intentionally written only to a small subset of the available cylinders.
And usually the outermost cylinders, right?
Typically the first 30 to 40%, starting from the outermost tracks, yes.
Why the outermost tracks?
Remember zoned bit recording? The outermost tracks have the highest data density, meaning the drive can transfer more data per revolution. So by limiting the movement to this high-speed, high-density area, you simultaneously maximize the internal transfer rate and drastically reduce the average seek time.
Because the actuator arm never has to travel the full distance.
Never. It's only moving across a small fraction of the platter surface.
So what was the real-world trade-off for this massive performance gain? It sounds too good to be true.
The trade-off was brutal. A significant sacrifice of usable storage capacity. A 500 gigabyte drive might be logically configured and treated as a 200 gigabyte drive just to achieve sub-4 millisecond average seek times.
Wow, you're throwing away more than half the drive.
You are. But this technique was historically indispensable in environments like high-frequency electronic trading systems. There, the ability to retrieve market data a few microseconds faster was literally worth millions of dollars.
So the loss capacity was just irrelevant compared to the latency savings.
Completely irrelevant. It highlights that storage isn't just about capacity, it's a tool for business advantage.
Once the head is positioned over the correct track, we run into the second mechanical delay. Component 2, rotational latency. The wait.
The wait. That's a good way to put it. Rotational latency is the inevitable time delay taken for the platter to spin and rotate the specific requested sector directly underneath the now stationary RW head.
I like the baggage carousel analogy. You're at the right spot, but you have to wait for your bag to come around.
That's a perfect analogy. You're at the right track, but you have to wait for the rotation to bring the data segment to you.
And since the head movement is random, the wait time is, on average, half a rotation.
Always. The average rotational latency is always calculated as 1/2 of the time required for a full revolution. And this delay is unavoidable in every single random access operation. If you requested 10 random data blocks, you would incur 10 separate seek time penalties and 10 separate rotational latency penalties.
The comparison between drive speeds really makes the latency impact concrete.
It does. Let's look at the delta between common speeds. A desktop drive spinning at, say, 5,400 RPM requires about 11.1 milliseconds for a full rotation.
So the average latency is about 5.5 milliseconds.
About 5.5, yes. Now compare that to a top-tier 15,000 RPM enterprise drive. Its full rotation takes only 4.0 milliseconds.
Reducing the average rotational latency to just 2.0 milliseconds.
Exactly. That 3.5 millisecond saving, when you multiply it across thousands of transactions per second, is the difference between a high-performing system and one that is perpetually constrained by its storage.
Finally, after all the seeking and the rotating, we get to component 3, data transfer rate. This is the throughput, the speed at which the data actually moves off the disk and into the host system.
Right, the actual payoff. The data transfer rate refers to the sustained amount of data per unit time that the drive can deliver to the host bus adapter, or HBA. But we have to break this down into two distinct rates because they are limited by different factors.
Okay, so the first one is the internal transfer rate.
This is the speed at which data moves from the platter surface through the magnetic heads and into the drive's own internal buffer or cache. And this rate, as we discussed with ZBR, is highly variable.
Right. Faster on the outside, slower on the inside.
Exactly. And importantly, this internal rate is momentarily paused during every single seek operation.
And the second one is the external transfer rate.
This is the rate at which data moves from that high-speed internal cache, the drive buffer out through the physical interface, like SAS, SATA, or Fiber Channel, to the host, HBA.
And this is often the big number they advertise on the box.
It is. It's often the advertised interface speed, which is usually a burst speed, achievable only when the data is already waiting in the drive's buffer. The true sustained external transfer rate is typically governed by the much slower internal transfer rate from the platters.
So you can never move data out faster than you can mechanically pull it off the spinning metal.
That is the bottom line. You can't.
So putting this all into perspective, the fundamental reality for anyone dealing with HDDs is that the mechanical component is the absolute performance ceiling.
It is the unavoidable speed barrier. The takeaway is this. For any workload characterized by high random I/O, which includes almost all transactional databases and operating system file access, the performance is crushed by the perpetual penalties of seeking and rotational latency.
Even with big RAID arrays.
Even with massive RAID arrays built with dozens of HDDs, they can't circumvent these foundational physical limits. The industry eventually hit a wall here, which is precisely why the pivot to non-mechanical storage was, well, inevitable.
Here's where we see the industry overcoming those physical constraints. When high-performance applications like algorithmic trading platforms or massive-scale web services simply couldn't tolerate multi-millisecond mechanical delays anymore, the solution was revolutionary.
It was.
Eliminating motion entirely. We moved to solid-state memory, resulting in flash drives or SSDs.
The shift to SSDs was a paradigm shift. I mean, it's comparable to moving from horse-drawn carriages to automobiles. The bottleneck was physical, and the solution had to be electronic.
So let's discuss the core principle of the architectural shift. What's the big idea?
The single most impactful design change is that SSDs use semiconductor-based solid-state memory, specifically non-volatile NAND flash memory. This choice instantly vaporizes the two defining mechanical delays of HDDs.
So there is no seek time.
Zero seek time, and no rotational latency. Data access is purely electronic, governed by voltage and the speed of silicon.
And what does that translate to in terms of real-world performance metrics?
The results are astounding. Instead of latency measured in milliseconds, SSDs operate in microseconds. That's 1,000 times faster. Performance is measured not by how quickly a head can move, but by the raw ability to handle a high volume of concurrent requests.
So we're talking about IOPS.
We're talking about delivering massive numbers of IOPS, input-output operations per second. A standard enterprise SSD might deliver 500,000 random read IOPS, while even the fastest 15,000 RPM HDD struggles to hit maybe 400 IOPS.
That's a staggering difference.
It's transformative. It's a different class of device entirely.
That low, stable latency makes SSDs ideally suited for workloads that HDDs could never handle efficiently.
Absolutely. The ideal workloads for flash technology are those requiring consistently low latency and high random access performance, especially with small block sizes. Think mission-critical systems.
Like real-time analytics databases.
Real-time analytics, intensive transactional databases, OLTP, server boot volumes, and virtualization platforms where rapid metadata access is absolutely paramount. And they also provide benefits beyond speed, specifically in efficiency.
Right, a lower power consumption is a huge factor in scaling up data centers.
It's crucial. SSDs consume significantly lower power than mechanical drives, particularly under load, because they don't have to spin platters or move actuator arms. This reduces energy costs and, critically, the cooling costs in massive scale environments.
So they can have a lower total cost of ownership at scale, even if the initial price is higher.
That's often the case, yes.
So if the HDD is defined by its mechanics, the SSD is defined by its electronic intelligence. Let's look at the key components of the flash drive architecture, starting with the heart of the storage medium, mass storage or NAND memory.
NAND flash memory is the non-volatile storage grid. It's an array of transistors that store data by trapping an electrical charge. But critically, we need to understand the fundamental trade-offs inherent in NAND by looking at the NAND cell types.
This is where we get into the density, endurance, and speed characteristics of the storage cells themselves. This is where we move beyond the basic definition and really understand the cost versus performance spectrum.
Exactly. There are 4 major types defined by the number of bits stored per cell. First, you have SLC, or single-level cell.
1 bit per cell.
1 bit per cell. It is the fastest, most reliable, and offers the highest endurance, the most write cycles, but it is by far the most expensive and has the lowest density. You see it almost exclusively in extreme enterprise environments.
Okay, then there's MLC.
MLC, or multi-level cell. It stores 2 bits per cell. It doubles the capacity, but it lowers the endurance and speed compared to SLC.
Why is that?
Because the controller has to manage 4 distinct voltage states instead of just 2. It's more complex, so it's slower and wears out faster.
Then we get to TLC and QLC, which are more common now.
They are. TLC, or triple level cell, stores 3 bits per cell, which is 8 voltage states. This is the current standard for consumer and general enterprise drives. It offers high capacity at a moderate cost, but with significantly reduced endurance compared to SLC or MLC.
And finally, QLC.
QLC, quad level cell. 4 bits per cell, meaning 16 voltage states to manage. This offers the highest density and the lowest cost per gigabyte, so it's ideal for bulk, read-intensive archival storage. But it has the lowest endurance and the slowest write performance of all.
This breakdown really clarifies the trade-off system administrators face. You can't have ultra-low cost and ultra-high endurance in the same device.
You absolutely cannot. And this density decision directly impacts the longevity of the drive because every NAND cell has a finite limit on the number of program erase cycles it can endure before it fails to reliably hold a charge. This leads us directly to the brain of the SSD, the controller.
The controller. This is the embedded processor, the crucial piece of proprietary logic that manages the entire flash architecture. What makes this controller so much more sophisticated than an HDD controller?
It has a vastly more complex task because of the nature of NAND flash. While an HDD can overwrite data directly onto a sector, NAND flash cannot do that.
You can't just change a 1 to a 0.
You can't. You can only write data to empty pages, and you can only erase data in large predefined blocks, often 4 megabytes or larger. This necessitates a complex series of processes handled by the controller, chiefly the flash translation layer, or FTL.
The FTL is perhaps the single most important concept in understanding SSDs. What is its core function?
The FTL is firmware logic that maintains a sophisticated map between the logical block address, the LBA requested by the host, and the actual physical location within the NAND chips.
So it's another layer of abstraction, like LBA was for CHS.
A much more dynamic one. Since the controller must constantly move data around to perform wear leveling and garbage collection, LBA 100 might map to physical address X 1 minute and physical address Y the next. The FTL hides all of this physical movement from the operating system.
And this movement is necessary for 2 critical processes you mentioned, wear leveling and garbage collection.
Wear leveling is vital because NAND cells have finite endurance. The controller has to ensure that write operations are spread evenly across all cells in the drive to prevent any one block from wearing out prematurely.
And garbage collection.
Garbage collection is necessary because of that write limitation. To update just 4 KB of data, the controller can't just overwrite it. It must first read the entire 4 MB erase block into its cache, modify that 4 KB page, erase the entire original 4 MB block, and then write the modified 4 MB back to a new, empty location.
That process, the read-modify-write cycle, that explains why SSD write operations are inherently more complex and slower than read operations, even though the drive is so fast overall.
It is the fundamental technical challenge of flash. It's a huge amount of background work. And it also explains why an SSD needs specialized memory management components.
These components include standard high-speed RAM and crucial non-volatile RAM, or NVRAM.
That's right. The standard RAM is used as a cache for the FTL mapping table and for temporary storage of data during that complex read-modify-write cycle. This cache significantly speeds up access.
But if the power goes out, that RAM is wiped.
And if that crucial FTL mapping table is wiped out before being saved, it could lead to corruption and total data loss.
And that's where the NVRAM comes in, linking the hardware directly to the disaster recovery planning we mentioned at the start.
Precisely. NVRAM, or often a system of capacitors, sometimes called PCAPs or power capacitors, is integrated into the SSD design specifically for power loss protection. If power is suddenly cut, the NVRAM or the charged PCAPs provide just enough power.
Just a few milliseconds worth.
Usually just milliseconds worth, yes. Just enough for the controller to quickly save the current FTL map and any critical buffered write data from the volatile RAM cache down into the non-volatile NAND memory before the system completely shuts down. It ensures data integrity, and it's a non-negotiable feature for enterprise-grade flash storage.
If we connect this all to the bigger picture, the SSD represented a fundamental leap. It didn't just slightly improve performance, it completely redefined where the storage bottleneck even is.
It changed everything. By eliminating the mechanical limits, the bottleneck shifted entirely. Storage systems could now handle I/O demands that were previously impossible. Instead of the drive mechanism being the slow component, the limiting factors moved. They moved to the sophistication of the controller logic, the speed and efficiency of the FTL, and the capabilities of the host bus connecting the drive.
So it became about the path of the data, not the location of the data. We've taken a comprehensive deep dive into the architecture of storage, spanning decades of engineering evolution. We meticulously broke down the mechanical HDD into its constituent parts platters, tracks, sectors, and cylinders, and detailed the unavoidable performance delays imposed by the physics of seek time and rotational latency. We contrasted that mechanical complexity with the pure electronic speed of flash drives, exploring the NAND architecture, the complexities of the FTL, and the crucial differences between SLC and QLC cells.
For you, the learner, these details are the essential context needed to make informed decisions about infrastructure. Always remember these key takeaways.
Okay.
First, HDD performance is physically limited. Every random access operation pays the unavoidable tax of seek time and rotational latency. Optimization techniques like short stroking tried to mitigate this, but they never eliminated the root cause.
The second.
Second, abstraction is fundamental. Logical block addressing, or LBA, made large-scale storage possible by abstracting the complex physical geometry, CHS, away from the operating system.
And third, the SSD.
Third, SSDs overcome physical limits. Flash drives eliminate mechanical delays, offering ultra-low latency and incredibly high random IOPS, critical for modern high-transactional applications. But they also introduce new complexities like wear leveling and the read-modify-write cycle, all managed by the intelligent FTL.
This journey illustrates that engineering solutions often involve entirely changing the problem space rather than just incrementally improving an outdated mechanism.
Indeed, and this raises an important question that defines the next frontier in storage infrastructure. Since high-speed flash drives have largely solved the local latency problem within the drive itself, what becomes the single biggest systemic bottleneck when we start aggregating hundreds of these high-speed SSDs together in a vast storage area network or a hyper-converged cluster?
Interesting.
If the drives themselves are no longer the bottleneck, what part of the architecture is now failing to keep up with the torrent of data? Hint, it's the highway, not the destination.